So I want to go over vector functions and space curves, and basically what you have here is exactly what this graph is right here from the book. You have a curve that's going through space, okay, and as it's going through space, you have vectors that are describing it. Let me draw the curve with the purple, okay. So as the curve is going through space, you have vectors that are describing it. So essentially, the endpoint of a vector will determine the points on the curve. Endpoint of a vector will determine the points on the curve. So if you have, for example, something easier than this, let's say you could have a circle in space, and you could have vectors. The way that you describe that would be vectors pointing up to the circle. And so the endpoints of vectors gives us the curve. So these are called vector functions and space curves. And you've dealt with this before. All it is basically, you've seen this before when you dealt with lines and planes. You would describe a line with as a vector function, and not necessarily a plane, but a line. And so you were really working with vector functions without even knowing it. So it's a pretty simple concept. You may have a function, so a vector function. A vector function is a function that maps numbers to vectors. So basically, you've seen functions in algebra before, but they looked a little different there. Like you would have x squared, and like 3 went to 4, and 5 went to 25, things like this. But now, instead of having numbers over here on the right, you have vectors here. So numbers go to vectors. So t-values go to vectors. So let me draw this differently. Let me draw a big box instead. So these are t-values, if you want. This, whatever variable you want. And maybe your vector function is t squared, t cubed. So then you would end up with a vector 3, 9, 27. And you would draw that point in space. And then for 5, you would get 5, 25, and 125. You would draw that point in space. And so whatever that would look like, your first vector would be 3, 9, 27 over 3 of 9, 27. So it might be a vector like this. And then your second vector might be a vector like this. And then you just connect the dots. You have a lot more of these, of course, and you have a space curve of some sort. Okay, so let's go look at examples of this. Let's see what we got here. Sketch the curve to get a vector equation. Let's see, I think 7 might be good. So 7 says r of t is t sine t. It's an easy way to do this. If you look, this is x and this is y, so y equals sine of x. This is your good old friend y equals sine x from trig. So you just draw that curve. But what's making this curve is a bunch of vectors. You don't need to draw them, but essentially what's happening is there's a vector here, there's a vector here, vector here, vector here. That's not so much a line. There. And let me show you what's going on kind of behind the scenes here. You have a t value, and you have a sine of t. Well, r of t value, r of t. Okay, so when t is 0, r of t is 0, comma 0. When t is pi over 2, you have, let's say pi over 6. You have pi over 6, comma 1/2. So you're going to go over pi over 6 up 1/2. If you have pi over 2, you have pi over 2, comma 1. Well, these are just points on the sine curve. It's just the sine curve there. So it's really the kind of the same stuff you've seen before, in 2 dimensions at least. If you look here, this is just a line. Number 9, it's just a line. We had that, let's see, x is t. Let's just look at it here. X is t, y is 2 minus t, and z is 2t. So you had a vector that was parallel to the line, which was coefficients of t. And then the point on the line would be the constants in there. So there's 0 for x, 2 for y, and 0 for z. So this is the line that is parallel to this vector v, and it goes through this point. It's really stuff you've seen before. Now, if you look at number 11, though, 11, it's a little different. Let's pull this one over. 1 cosine t, 2 sine t. So 11 says r of t is 1 cosine t, 2 sine t, like this. So what's happening here is x is always 1. So in the x, y, z axes, x is always 1. So whatever this thing looks like, it lies in the plane x equals 1. Remember, that's the it's this line x equals 1 in 2 dimensions. That's just that's this guy right here, and then it's just repeated over and over and over and over, up, going up. All right, now we have this. So y is cosine t. Let me draw this in a different color. Y is cosine t, and then z is 2 sine t. And then you can kind of try to relate these. If you look, you can do, divide z by 2, you get z over 2 equals sine t. And then, so I'm going to erase this piece. And if you notice, y squared plus z squared over 4 is 1, because on the right would be cosine squared plus sine squared. The right is cosine squared t plus sine squared t. You square both sides, so you get y squared and z squared over 2 squared. Well, this is an ellipse. This is an ellipse. So basically you have an ellipse that's further in the z direction that lies in the plane x equals 1. So it's now this x equals 1 doesn't stop at the bottom here. So this ellipse goes something like this. This here is below the xy plane, and so that's essentially what you have here. I don't need to draw that. This goes further down like this, all the way down. All right. A better way to draw this would be drawing with dotted lines instead, something like this. Something like this. And all right, so that's that one. All right. You just try to relate the x, y, and z's together. If you look at number 10, 10's a good one too. Sine, yeah, okay, so number 10 would be 10 r of t sine of pi t, and then t, and then cosine of pi t. All right, so let's relate x, y, and z together. Well, if you look, x squared plus z squared is sine squared of pi t, plus cosine squared of pi t. Well, sine squared plus cosine squared is always 1, so x squared plus z squared equals 1. So this lies in it lies on the cylinder, so this lies, so r of t lies on the cylinder, x squared plus z squared is 1. So whatever this looks like, it's going to be in this cylinder. Here's x, here's z. There's a cylinder here, like this. See, there's no y, so the rulings are parallel to the y-axis. And then what's going on with y? Well, y is t. So whatever t value you have, y is just going to follow it. So the circle, this is going to be a spiral. So watch. Here we go. Here we go. Here we go. So let's pick some t values. So t versus r of t. So if you look t, when t is 0, you get, I'm looking at this up here, you get 0, 0, and then cosine of 0 is 1. So this starts out at 0, 0, 1, which is up here. Let me draw, well, I'll draw it. Let me draw it in red. And then when t is pi over 2, we get 1, pi over 2, and then 0. So then we go out 1, out pi over 2, and up 0. So maybe that's here. And then at pi over, at just pi, we get sine of pi is 0. I'm looking at this. Sine of pi is 0. Then we get pi. And then cosine of pi is negative 1. So we go over 0, out pi, down 1. So now that is maybe underneath. So down here somewhere. So it's doing this. So I would invite you to kind of test this as we're going around the circle. See, x squared plus z squared is 1. You never really in algebra you're never really taught that what you can do is you can have a circle with a direction. As we're drawing out the circle, y is picking up the pencil and pulling it in the y direction. This is the y direction here. All right. So if you need more help on that, see the book. The book has a good example of that. And so that's that. So now, if you look at the matching, which I'm probably going to do quite a bit of matching in the on the test because it's just easier to just test you on that. I mean, drawing this stuff is kind of hard, but I do want you to know how to at least do matching. So if you look at these here, let's see, look at 21. 21. Wait, let's look at. How about 26? So 26 is a good one. If you look, x plus y is 1, because that's sine squared plus cosine squared is 1. So this is, whatever this looks like, it's going to lie on the plane y equals 1 minus x, or negative x plus 1. Negative x plus 1. So that line is here. Negative x plus 1 is here in the xy plane. And so when you draw that in 3 dimensions, okay, you get this. So that line there is right here. And well, that's a plane in 3 dimensions. Okay. So whatever this looks like lies in that plane. Now, if you look, z and y are related. Z and y are related. Let's see, z is, so y is sine squared of z. Y is sine squared of z. Now, if you've never seen sine squared before, it really just looks like sine, but it bounces up and down. looks like this. Doop, doop, doop. So instead of going under, it goes above because it's squared. And it's a little it's probably more peaked like this. All right, so that is in the YZ direction, and so we've got some sort of sine curve here, and the same thing goes with cosine and x. So it looks like x is cosine squared of z. And so we got to look for some sine and cosine looking curve in this plane here. And that's, I think it's this one here. If you look, this one will be in that plane. It's not so obvious, but this is that plane that I drew. All right, so that one's 3. So you just play around with these a little bit. And I think the WebAssign videos are probably pretty good at this, at showing you these. Okay, so let's move on. So this is a good one here. Oh wait, before I get to that, I want to show you a little bit about how Wolfram Alpha can help you out with this. So let's look at some of these. In the homework, it's going to ask you to graph some of these. Do your best to graph them, but really, it's pretty darn hard to graph this stuff. You kind of almost have to be led to it. So Wolfram Alpha uses the term space curve to graph. And so all you'd have to do if you had, for example, x equals, so your function would be r of t equals cos t sine t and then sine of 2t, like that. You just put that in for space curve, and the good news is that Wolfram Alpha will recognize this t as x or whatever you want. That's your variable. It knows it's variable. And so when you graph it, it looks like this. It's the potato chip one. So if you want, that one is this one here, number 1. So apparently this one, number 24, is number 1. All right, so let's do this one, cosine squared, sine squared, and t, see what happens. So here I have it. I've gone ahead and put it in already. Oh, I need another parenthesis in there. There we go. Parenthesis at the end. And let's see how it graphs it. Yeah, so it's not the best, but it kind of looks like at least somewhat similar to the one that we thought it was over here. This one here. Okay, so use that use that to graph some of your curves that you need. Now, it says here, find a vector function that represents the curve of intersection of the cylinder, x squared plus y squared is 1, and then the plane y plus z is 2. So x squared plus y squared equals 1 can be represented by x equals sine t, y equals cosine t. And then this goes back to parametric equations. And so hopefully you were able to review some of that. Now y plus z is 2. Well, if y plus z is 2 and y is cosine t, then we have z is 2 minus cosine t. And so the curve of intersection could be represented by r of t equals sine t, cosine t, and then 2 minus cosine t. So we take the cylinder and we slice it with this plane, and we get this curve here. And the curve is sine t, cosine t, 2 minus cosine t. Okay. This is from the book. I'll let you read it. All right, so here's a good problem that you probably see on a test. It says, show that the curve of parametric equations, those lies on the cone, and use this fact to help sketch the curve. Well, we have a cone here. Let me blow this up a bit. Well, if these equations lie on the curve, on the cone, then when you plug them in, it better work. So you have z squared equals x squared plus y squared, which means then that if I use z as t, we have t squared equals x squared now would be t squared cosine squared t plus t squared sine squared t. And if you take that t squared out of the right, you get cosine squared t plus sine squared t. And this is all just equal to 1, so we get t squared equals t squared. And there you have it. So now we've got to sketch the curve. So it's on a cone. It's on a cone. So we draw the cone. And this is my axes. This. And then when you draw this, if you look, it's t cosine. So let's see, x squared plus y squared, that'll be t squared. So there's a circle going on here. And z is a constant. So let's try 28 now. So 28 says, let's see, we got x is sine t, and then y is cosine t. So right away I know that it lies on the cylinder x squared plus y squared equals 1. So this is a cylinder going up like this. Okay, now z is sine squared t. So this means that if you look at x, pull x down, z is x squared. Z is x squared. So that is a paraboloid. I'm sorry, it's a parabolic cylinder going parallel to y. So that's going like this. And then, so this is the y-axis this way. So y-axis, x, and then z comes up this way. And then I think that's good enough for now. So it's the intersection of these two. When you intersect these two, it's kind of hard to see it, but you get kind of a potato chip. It's kind of hard to draw. Tell you what, let's have Wolfram Alpha help us with this. This was another one. So x is sine. Here's what we get. So when I plug it in, so let me press enter here, see what happens. Computing. Yeah, it's potato chip. Now, if you have the Pro, you can move that around, but I don't. All right, so that's that. So let's see what's next. So it says use a computer to graph. You can do that. And then find a vector function that represents the curve of intersection. So these can be kind of difficult. Let's try one though. Let's try number 40. So when you have x squared plus y squared equals 4, you can let x equal 2 sine t, y equals 2 cosine t. When you square these, you get 4. So far you have x and y. And if z is xy, that means then that z is 4 sine t cosine t, which is just 2 sine 2t. This is because let's break this down a bit. Let me just draw like this. Z equals 2 sine t 2 times 2 cosine t. I'm going to pull one of the 2's. I'm going to pull the 2's out. So this is 2 times 2 sine t cosine t. Now 2 sine t cosine t is sine 2t. So this is 2 sine 2t. And so our curve, using all this, our curve is r of t equals 2 sine t, 2 cosine t, and then 2 sine 2t. Like that. there you have it. So this one here is going to be sine squared plus cosine squared is 1. So you have x equals, so let's look at 43. X equals sine t, y is cosine t. And then it says z is x squared minus y squared. So z is, actually I bet if we flip these around, it doesn't say we can't. It's cosine squared plus sine squared is still 1. So then z is going to be cosine squared of t minus sine squared of t. Well, that's just cosine of 2t. That's why I want to flip it around, because it's obvious. And so my vector function here is cosine t, sine t, and then cosine of 2t. Now, if you switch these two around, this one becomes negative, and you're going around the cylinder a different way. Okay, so if you look, let's look at r of t. Let's take out that third part. R of t is cosine t sine t. Okay, so that's the circle that starts at, when t is 0, you have 1, comma 0. So this starts here at 1, 0. Let me blow this up. Here at 1, 0. And then when t is pi over 2, you get 0, 1. So it's 0, 1 is there. So it's going in this direction. This direction. Okay. Now if you switch those around, so suppose you had s of t is sine t cosine t, then these numbers, these points flip. So first comes 0, 1, and then comes 1, 0, and so it's going around. So sine cosine is clockwise, cosine sine is counterclockwise. It's important that you know that. All right, any more? This is derivatives and integrals of vector functions, and we'll get to that